Today's goal is to sketch exponential functions. And so a guiding question throughout this class is, well, what makes a good graph? Because different functions have different features. Is there anything that unites really good graphs of good functions? I would argue that you need three characteristics. You want to find and plot intercepts. You want to make the domain and range apparent and make the shape apparent. So for example, if we were sketching the radical function in the last unit, 3 root x plus 1. Well, a good sketch would make it clear that this has a vertex and an intercept, a y-intercept coincidentally, at the point 0, 1. And we can tell from the shape it's got this increasing at a decreasing rate shape. It's going up all the time, but the rate at which it's going up is going down. And we can see that from the vertex, it has domain 0 to infinity and range 1 to infinity. We can tell which x and y values are coming into play here. Or the related quadratic function, 3 root x plus 1 squared. This guy has a vertex at -1, 0. And we know that a quadratic function is shaped like a parabola. So we should also find its y-intercept. But you can see here we're using all x values possible. It's continuing forever to the left and to the right. And it's starting at the y value 0 and then going on up forever from there. Whereas the function y equals 2x cubed, the cubic function has domain and range all real numbers because we know its shape. So if we want to graph an exponential function, we need to know what their shape is, and we need to know what their domain and range is. So what would that be? Well, let's take a look at the parent function. The parent function would be f of x equals e to the x, but I don't know about you, I don't know offhand what e squared and e cubed and e to the fourth are, so maybe we can just round. We'll use a proxy parent function, f of x equals 3 to the x. And if we want to know what it looks like, sometimes it helps to start by making a table of values. For example, 3 to the 0 is 1. 3 to the first is just 3. 3 squared is 9. And 3 cubed is 27. Okay, we can get a sense of, oh wow, these y values are increasing really dramatically. Well, what about 3 to the -1? 3 to the -1 is 1/3. And 3 to the -2 is 1 over 3 squared, so that's 1/9. And 3 to the -3 is 1 over 27, 1 over 3 cubed. So these y values, as we head this direction, are getting smaller and smaller. And in fact, 1/27 is a very small number. It's basically negligible, or very close to 0. And so that's why this function has the shape like this. If you're to plot these points, right, the y values get very large very quickly as you move to the right, or as x approaches infinity, and as you move to the left, or that is as x approaches negative infinity, these y values are going to get closer and closer and closer to 0 without ever touching it. So this function has a horizontal asymptote, which makes it clear that the range must be from 0, not including 0, up to infinity. But you can put any x value into the exponent. Negative numbers, of course, you can make the negative exponents positive by moving that term to the denominator. And since you can put any number into an exponent, the domain is all real numbers. So what shape does this function have? It has sort of this curved shape. And what characteristics dictate its domain and range? Well, the range is dictated by the horizontal asymptote, that line that your function approaches but never intersects. Let's put this into practice with a couple of examples. First, we'll sketch the function f of x equals 5 times 3 to the x minus 2. So we want a couple of things. First, we want to find the intercepts. To find the x-intercept, we set y equal to 0. And we know that this is now an exponential equation, which we'll be able to convert into a logarithmic equation in order to get that x out of the exponent once we've isolated the base and its exponent. So we need to first move this 2. And now move the 5. So we have 2/5, or you can write it as a decimal if you prefer, is 3 to the x. This is my base, the term holding up the exponent. This would be my exponent, and this is my argument. So we're going to put it into logarithmic form. So the log base 3 of 2/5 is x. I can use my calculator to approximate the log base 3 of 2/5 is about negative 0.834. So that's our x-intercept. Let's find a y-intercept by setting x equal to 0. And anything to the 0 power is 1. No need to check for extraneous solutions. That's only if we're solving radical and rational equations. So we're done finding intercepts. We also need to make sure the shape is clear and the domain and range are clear. Well, the range is dictated by the horizontal asymptote. And we can tell that this minus 2 means that the parent function, or the similar function 5 times 3 to the x, has had a vertical shift 2 units down. And so instead of having a horizontal asymptote at y equals 0, we're going to have a horizontal asymptote just on the left-hand side at negative 2. So we'll mark that in. Let's go ahead and plot our points. We have the y-intercept 0, 3, and the x-intercept negative 0.834. Let's make it clear that we understand the shape of an exponential function looks like this. And oops, didn't mean to do that. That shape allows us to see clearly we're using all real x values. The domain would be negative infinity to infinity, and that we're using the y values above the horizontal asymptote. So the range would be from 2 to infinity. Okay, 2 more examples to look at tonight. Here's our function 4 to the x plus 5. We'll again start by finding the x and the y-intercepts. X-intercept can be found by setting y equals to 0. This is an exponential function, exponential equation, so we're going to solve by isolating the base and then converting into a logarithmic equation. Now, when you type this into your calculator, you should get an error message because the log function isn't defined when you have a negative argument. You don't have to memorize that at this point, but you should know that if you get an error, that means that there is no x-intercept. Okay, well, let's look for a y-intercept by setting x equal to 0. Anything to the 0 power is 1. So here's our y-intercept. Now, to make the domain and range clear, we have to notice that the function has been vertically shifted up 5 units. So this time there's going to be a horizontal asymptote just on the left-hand side at y equals 5. So let's go ahead and plot those values. Make it clear that our function is going to get closer to the horizontal asymptote at the left-hand side and then increase dramatically on the right-hand side. And now we can see from the graph why it makes sense that we wouldn't have an x-intercept because our horizontal asymptote is above the x-axis and we're increasing from there. So it would have no opportunity to touch or intersect the x-axis. Okay, last one for today. Let's find the x-intercept. By isolating the base and then converting to a logarithmic equation. Again, feel free to use your calculator to approximate this value. Of course, you wouldn't know how to do it by hand. Neither do I. Okay, so here's our x-intercept. Let's find the y-intercept. Oh, this should have said f of x. Sorry for the typo. And we must know the horizontal asymptote. We can tell that the function has been vertically shifted up 3 units, so we'll have a horizontal asymptote at y equals 3. Let's put these pieces together. Now this is interesting. This time we must be below the horizontal asymptote. Why would that be? Oh, that's because this negative sign creates a reflection across the x-axis. So instead of having the shape like this, it's been reflected, so it should have this shape. Well, that's consistent with what we found for the intercepts and the asymptote. So here is our final sketch.